Welcome to Griffith Institute's Innovare Elevation Series, where we're always exploring the latest innovations in technology. Today, we're excited to introduce you to Murray Tom, Vice President of Quantum Business Innovation at D-Wave. With over 20 years of experience in the quantum computing industry, Murray is a recognized expert in the field. In previous roles at D-Wave, Murray was responsible for the development and delivery of the Leap Quantum Cloud Service and the Ocean open source tools. He's led teams engaged in customer projects related to algorithms, applications, and performance testing, and has even assembled a few quantum computers by hand. At D-Wave, Murray leads the Quantum Business Innovation Team, which is focused on helping customers and partners leverage the power of quantum computing to solve the most pressing problems. I'll ask our audience to ask your questions within the chat area, and we will try to address them at the end of the presentation. Murray, we're looking forward to hearing more on the opportunities at D-Wave and the exciting insights you'll be sharing with us and the Innovare community. The floor is yours.
Thanks, Melissa. And thanks everyone for joining. It's great to be here to share with you about quantum computing, the technology and the use cases, how people are putting it to use right now. So I'll just pull up my presentation, and this is going to be a lot of fun. So let me begin by talking about the fact that D-Wave is the practical quantum computing company. Our main focus is to make it just as easy to build applications with quantum computing technology as it would be to build an application any other way in order to help you solve some of your most challenging mission problems. Now, in my role at D-Wave as the Vice President of Quantum Business Innovation, my responsibility is to help you to create mission value using quantum computing technology and to put it to practical use. So let's begin in this presentation asking the simplest question, which is like, what is a quantum computer? So there are there's a lot to it that we can kind of dive into, but the important thing to think about is that it's a device that's going to use quantum effects in order to accelerate information processing. And in that way, think about it as like the quantum effects are like a resource to you. So once you have that idea to build a machine that's capable of doing that, there are multiple models of how to use those quantum effects for doing useful work. One of them is to allow your computer to store more information and to process over that information. It's very powerful. It's also quite fragile, and it's going to enable applications in areas like solving differential equations or doing quantum chemistry simulations. So that model is called the gate model of quantum computing. And what's fascinating about it is that you're actually putting information into the quantum states. So the thing to keep in mind there is that if the quantum states collapse, that information gets lost. And that's why that model of quantum computing includes error correction in order to help you to recover that information in its operation for those applications that it's going to be used for. There's another primary model of quantum computing, which is called annealing. And in annealing, the notion here is that the resource of the quantum mechanics is to allow you to move between solutions quickly. So that's going to be really important when you're tackling problems where you have a large space of solutions to look through. So let's have a look at this in a little bit more detail here. So I talked about the gate model and the applications that that's really suited for. In annealing, the notion here is that the solutions I'm describing, imagine you're working on like a large scale logistics application where you need to coordinate a set of drivers who are basically delivering materials to a set of sites that need them. The plan for all the drivers and the routes they're going to be driving is one solution. So each of those plans can involve a driver like picking up one delivery or substituting one of the deliveries with another driver. Those are the different solutions that the quantum computer is helping you move through. And if the quantum state collapses, then you basically stop on one of those plans, and that's actually operable information. That's information you can use in your application. The interesting thing about that model is that if you hold it there, the quantum state will reemerge and it'll continue to looking through solutions, continuing to work for you to help you find a better one. So really, those are two models. They're sort of ways of using quantum effects to help you do useful work. And the important thing is to recognize is that those models are maturing at different rates. The model associated with annealing is allowing us to build quantum processors and make them available in live cloud cloud platforms right now to help you build and power production scale applications. The technologies associated with gate model quantum computing are probably about 7+ years away from commercialization, and D-Wave is the only company that has sort of an expanded product set that's including both of these models of quantum computing. Now, a little bit about D-Wave. We were founded in 1999. We've got a little over 200 employees, and we're a full stack quantum computing company. So we've got a variety of customers across the commercial, the academic, and the government space, working on a variety of applications and mission applications. And we're, I'll just point out, we've got 220 US granted patents. The reason for highlighting that is that we're not an integrator of other people's technologies. We've actually developed all the core technologies that we need in order to be able to build, the quantum processors themselves and the rest of the technology stack that allows you to quickly and effectively build applications that are able to incorporate quantum computing technology to help you get the best results that you can in the challenging applications that you're working on. So when I say full stack, these are kind of the elements that distinguish, D-Wave, let's say, from the rest of the quantum computing industry. So we have built and commercialized 5 generations of quantum computing systems, culminating in our Advantage quantum processors, which right now have 5,000 qubits. And the qubits are interconnected with 15-way connectivity. So this is sort of like the powerhouse core technology of what D-Wave is developing. Now, in order to get you access to those quantum computers, we have built a quantum cloud platform which gives you immediate access, real-time access to these systems. You can program them and get responses back in seconds. And that's really, you don't have to schedule a time on the quantum computer later in the week. You can get access right away. Any of you can log in right now, search up D-Wave Leap, and you'll get access to that platform, and you could try out the systems, run the live illustrated demos there. There's even an integrated developer environment with a set of code examples that have been built to help you kind of get jump-started in the programs that you can develop with our quantum computing systems. The other thing is that in order to kind of make the formulation of application scale problems easier and handle application scale instances, we have developed hybrid solvers there, which combine the best capabilities of the quantum computers and classical computers as they're working together to create solutions for your mission problems. And I'll talk a little bit more about that a little bit later. As you're building that software for your applications, you're building on the Ocean Software Development Kit. This is an open source Python SDK, and it's available for local download or for use in the integrated developer environment right in Leap. And so, you can just think about this as like regular Python programming as you're basically expressing the objectives that you're trying to reach in your mission application and the constraints that you're trying to satisfy on your way to creating that solution. And lastly, we have a program, our launch program, which is really about helping to accelerate you on this quantum journey. So whether you're doing problem discovery and you're trying to work out, okay, where are the areas in our mission where quantum computers can provide benefit or where they're going to have an increasing impact in terms of the results obtained there, or you're at the scale where you're building a proof of concept with application data in order to sort of demonstrate for your organization, okay, this is how we can run this. This is the quality of results that we can get. Or whether you're taking it through like a limited production release to a full production release, that launch program is meant to help you through that process as quickly as possible, help you with the change management in order to be able to get those more effective results in your applications at scale. So with that, I have spent a fair bit of time out talking with software developers about quantum computing, and the difference that you get when you're talking, let's say, to a physicist versus when you're talking to a software developer is that a software developer will sort of say, if I know what I can use a quantum computer for, I would be more interested to learn about the technology itself. So let's begin right there. Let's talk about the use cases and what people are doing with our quantum computing systems. So here is a set of some select government use cases. At D-Wave here, we work with the Australian DoD demonstrating an application in last mile resupply. So this is a scenario where there's a depot that's received, a set of food, some water, maybe some vaccines that need to be deployed at a variety of locations. And either through, autonomous vehicles like drones or with trucks, they need to be, the delivery schedules and routes need to be planned and routed. So we have actually, built a method for using our quantum computers as part of a solution, which coordinates the movement of, trucks on roads, respecting, one-way streets and turning circles, in order to be able to get those resources to the locations that need them. And it's set up in a way where you can weight the value of using particular routes based on whether there's rubble in that location or it's become a more dangerous situation. So you can provide kind of like weighted penalties or incentives for choosing particular routes as you're trying to get that mission complete. Davidson Technologies, I was the MC at our Qubits User Group conference in Miami in January. We were delighted to have Davidson Technologies there to talk about applications that they're investigating with our quantum computing systems, including a missile defense application looking at a configured response to a missile attack scenario where they looked at 67 million possible scenarios in approximately 13 seconds. A fantastically relevant and really motivating applications in terms of like the value of the solutions that they're developing there. GE Research has also done some fantastic work looking at applications in asset sustainment. So this is an application where you have a fleet of vehicles in a variety of locations, and you need to plan their maintenance and operation over a period of time and make sure that you have the right spare parts at the right repair locations in time based on the movement of that fleet of vehicles and what their schedule of repair needs are going to be. They're looking at those applications at the scale of 15,000 repairs with more than 100,000 potential workflows. So fantastic work that they've done. And also Savantex, that's looked at increasing the efficiency of operations at the Port of Los Angeles. So let me actually go into that use case in a little more detail. So the Port of Los Angeles was looking to basically improve what is effectively a mission application of increasing the effectiveness of operations in a constrained operating theater. So this is a port in a dense area. They only have a limited amount of area that they can operate in, and they need to get material through that limited area as effectively as possible. It's also a good example of the fact that, when you're trying to create application solutions like this, it's not enough to just have a technological solution. You also have to look at the port operations and sort of say, how can we bring the technological solution together with changes in how the port is operating in order to bring about these changes? And they managed to increase the amount of cargo that these large cranes, the rubber tag gantries, are handling by 60% each day. And while doing that, they also managed to reduce the truck turnaround time by 12%. And this is, deceptive because even at modest scales, these types of applications explode in complexity. This crane is moving up and down a line, and all of the containers that are placed there are first in, last out, because they're placed on a stack, one on top of the others. And so you have to look at, you have a set of trucks that are getting set to arrive. They're not necessarily arriving at exactly the scheduled time that they requested. And you have to determine what is the way to pick these containers off based on the trucks that we have available to get them loaded, minimizing the crane movements so that you've got the least amount of downtime, sort of shifting it up and down the line. So there's lots of applications like this, and I'm sure many of you can identify with the types of like logistical challenges of operating a system like this. Denso is a major auto parts manufacturer in Japan, and they have been doing a lot of work at looking and exploring applications that incorporate quantum computing technology. I'll sort of mention there was an inflection point in the development of quantum computers where, D-Wave, at D-Wave, we demonstrated an application quantum material simulation where we materialized that 3 million times advantage in using our quantum processors versus classical computing. But the significant thing that happened there was that 3 million times advantage came about in 2 product generations. So we went from not being able to solve the problem effectively to being 3 million times faster in 2 product generations. That's exactly the kind of signal that companies like Denso were looking for, because that radical growth in the capability of impacting these applications, they want to be able to act on that and get that benefit in their applications because they want to discover the areas where that can bring the benefit. So in on-demand taxi assignment, they were really looking at a scenario where in Kyoto, there's a number of taxi routes that are basically like pre-booked, and they're not really booked and scheduled in a particularly optimal way. They were able to use our quantum hybrid platform to actually show that, knowing that you have this information ahead of time, you can actually effectively coordinate across all of the bookings and reduce the computational time by 25%, while still reducing the drive time by 7% and reducing the distance that is traveled by 9%. So a fantastic result there. And they've been looking at a number of applications to do with mobility, and which both are relevant to like scheduling and logistical challenges, but also in terms of like mobility challenges, which I think have a lot of broad applications. So, what I've been talking through so far are, some select use cases, but at D-Wave, we've definitely noticed a trend where we're seeing a lot of interest across these three industries, looking at real world applications. In logistics, we're talking about, shipping container logistics, employee scheduling, last mile vehicle routing, just like we discussed. In the life sciences space, this includes things like protein folding, but also, with papers written by GlaxoSmithKline, but also in protein design, there's companies who have like quantum designed proteins, synthesized them, and then taken them to live virus testing against COVID-19. We're also looking at applications in clinical trial optimization. And in the finance space, it's about things where, you're looking at how do I optimize a portfolio so that I get the best return in reducing risk, or how do I model risk in these types of scenarios? So a very close connection there in terms of the mathematical techniques that they use and the types of problems that our quantum computers solve. But it's also been used there for like fraud detection, where you have a lot of data, and generally the data is like normal operating conditions, but occasionally you have malicious users, or you have folks who are basically trying to get by with fraudulent actions, and you need to be able to like pick out those patterns. And some folks have been using our system to help develop predictive models using our quantum hybrid techniques for feature selection, so they can get models that they can build effectively with small amounts of data, using that kind of a machine learning workflow, incorporating our quantum hybrid solutions. Now, I just want to mention here that the notion here is to make this as easy for you to build a productive application as quickly as possible. And so, in a sense, there's no need to learn quantum physics. The great thing about this is that you're getting the power of quantum computing processing, but with like a classical problem going in and a classical interpretable answer coming back out again. And the way that we're managing that is a coordinated, orchestrated workflow between classical computers and quantum computers, where you're submitting a large application scale instance. We're actually deploying classical cloud resources that are ingesting the whole problem and beginning to sweep over them in order to be able to look for opportunities to improve the solution. And where it gets to challenging segments, it breaks those pieces out, passes them to a quantum computer to be reconfigured, and then pulled back in. And that's how the quantum and classical systems are working together to help explore that solution space to get you a high quality solution quickly and effectively. And so there are methods here. There's a couple of different models, but the notion here is to allow you to express your objectives, the decision variables that you're trying to use, whether they're like true false decisions, or whether they're integer decisions or continuous decisions, like I need to put a bin into a vehicle, and I need to determine like which orientation am I going to rotate it in, and then I also have to determine like where in the vehicle is it going to be slid. Those are all sort of decision variables of different types. So these solvers are meant to allow you to express them natively. That makes the expression time and the programming time faster for you. It makes it easier to basically run those programs and submit them to these cloud resources, and the solvers do a better job of solving the problems. It's also enabling you to express the constraints that you need to satisfy, like the gross vehicle weight is, maybe 2,000 pounds or something like that. That you can express natively up to 100,000 constraints going into these solvers, and that capability makes it, faster for a small, effective development team to build applications quickly and focus on the problem that you're trying to solve. And I also want to talk about the fact that this technology and this technology stack that we're providing is built to enable you to run applications in production. So I mentioned our advantage quantum processors that are available in the cloud today. You can get access to those immediately. You can start, getting your Python programmers working on this right away. If you're working with our launch team, it's enough to just have someone describe the problem to us that you're trying to solve, and our team can help you put together the formulation using our open source code, and then provide that to you so that you can basically run it in your application. And we're also focusing this technology so that as our quantum processors develop, as that hybrid technology is developing, you are getting the compounding advantage from all of those developments in the application that you're building. So our Ocean tools are meant to use these quantum processors to allow them to select different quantum processors that are available in the cloud. Right now we have one that's in Vancouver, Canada, one that's in Los Angeles, our US in-region based system, and one that's in Germany. So there are techniques for basically allowing the system to quickly switch between quantum processors, and as is the case with our Advantage 2 prototype, to incorporate new quantum processors seamlessly without requiring any changes to your application code. And our hybrid solvers, we're committed to have those adapt to those new technologies as they're developing. That is a big part of our program here at D-Wave, is developing those so that you're getting the power of the sort of state-of-the-art algorithms and methods, both classical ones and quantum mechanical ones, to help you focus on the mission application that you're working on, and focus on getting high quality solutions there. Yes, okay, so let's take a pause here, and we're going to make a bit of a jump from what I've been talking to you about in terms of like use case applications and way that you can use the system. I want to talk to you about some exciting results that have come out in quantum computing that we've demonstrated, where we're actually able to directly connect the quantum effects in our processors and the way that they're accelerating optimization. So this paper just came out in Nature. For those of you who are interested in reading more about it, that's the title of the paper. This graph that I'm showing you on the right, if you think about it, on the y-axis here, I have basically the quality of the solution. So as they're moving down in the y-axis, the quality of the solution is getting better. So lower is better here. You're getting to higher quality solutions. And on the x-axis, along the horizontal here, we've got time in mixed units. So the steeper that the decline is, the faster that the solution quality is being improved. And what we're able to show here in measurement and theoretically is that these quantum processors are able to improve the solution quality faster than classical computing. We're doing this for hard problems. They're hard optimization problems. So they're the types of optimization problems that occur in neural networks and machine learning, and in the kinds of logistics and scheduling applications that I've just been describing to you. And so there's now really hard concrete proof, theoretically, and with backed by measurement results, that quantum processors are the best for this. So this is just, I think a further indication that the future of these applications is going to be hybridized between quantum and classical computers. And you're not really in a situation where you have to stare into a crystal ball and try to predict the moment where that's going to take over in your application. You can begin building on this right now and get that increasing benefit over time right away. So, this result has been significant because we're demonstrating, coherent effects, these performance scaling from coherent effects. And coherence really just means that your quantum processor is running a calculation without being interrupted. There's not even individual photons of light hitting it and interacting with it. And that's what's shown in this steep curve here, where those blue points and the blue line are basically directly over top of one another. This demonstration is with our commercial Advantage quantum processors. So these calculations were done in our cloud platform, interleaved with the calculations that our customers were solving. So this is really a direct measurement from the quantum processors that you'd be using with our quantum hybrid solvers. And what we've sort of shown here is that this is going to do, this is a demonstration in hard material simulation problems. So these are kind of like applied problems that we're working on. And the data here gives us design information about how we are going to be able to improve this advantage for you with future generations. As we can make changes in our technology to improve the coherence, you're going to see improved advantages in those applications and see that compounding benefit. So for those of you who want to take a deep dive, absolutely have a look at this. It's a sort of a watershed moment in quantum computing, and it really goes well alongside a lot of the other performance demonstrations that are sort of demonstrating advantages for quantum computers and applications of this type. With that, I want to thank you. If you've got more questions, absolutely, as Melissa was saying, put them in the chat box. It's been my pleasure. I hope I've been able to share some of my excitement about quantum computers, being able to turn this quantum physics into useful work for us so we can accomplish our mission applications more effectively. Ask more questions, and thanks very much for joining me today.
Murray, thank you for your time and fascinating presentation. I look forward to seeing you later this month at the Q4I Quantum Information Science Workshop here in Rome, New York as well. Thank you to our viewers for tuning in today. Be sure to visit our website for more updates on cutting-edge technologies being done here at the Innovare Advancement Center and within our Innovare community. On behalf of Griffiths Institute and the Innovare Elevation Series, thank you.